Ran out of time today. I'm going to go through the chapter with you just for a minute about the things that you need to pay attention to and those things that you don't need to pay attention to. So starting on page 547, you'll know the different forces, and what the force-carrying particle is called. And you'll kind of know the order of which things go. That's pretty intuitive, I think. And roughly the distance over which things can happen. We did a whole lot with the bubble chamber and cloud chamber stuff when we were talking about detectors for nuclear events and stuff, not just for elementary particles. And so the kind of analysis that we do there with bubble chamber pictures, I expect you to be able to do some of that. For instance, figure out the charge of the particle, explain how you know what the charge is, whether it's a light or heavy particle, things of that nature, just from what you see. And when things are associated with a decay and when they're not. For instance, you might be able to, wherever the interaction takes place, you might see a particle-antiparticle pair appear some other distance away and know that either a gamma or a neutral particle went up and created that. So pair production, positrons. With the energy we're dealing with, Compton scattering and the photoelectric effect are just tiny effects. Most everything, interaction of radiation with matter, is either gently knocking some electrons off so that you can create the bubbles in a bubble chamber, or it's just by electron-positron creation. Then we went through the history of the idea that the virtual particle being the origin of the exchange force for the strong, and they estimated just from the uncertainty principle that ought to have a mass somewhere between the electron mass and the proton mass. So it was called a meson, meaning half was in between. And then the first one that was found ended up having the wrong mass. And you should explain how you know what that mass is. And then you don't have to know the mass, so I provide those kind of numbers for you. And then how they found the real meson, which you should know about. And then we use the uncertainty principle a good bit. So mostly not in the delta P, delta X, but as the delta E, delta T being the minimum type of thing, or equal to H bar over 2 typically is what they say. Then we've got the classification of particles, and I'll give you that table, but you ought to remember which ones are mesons and which are baryons and which are leptons. First of all, so that it makes your work go a little bit faster, not to have to always go back and look it up. But I might erase that part of the table anyway. So challenge you to know what a hadron is, what a baryon is, what a meson is, and a lepton. We talked very briefly about neutrino oscillations, but never had a chance to get into it, and that's all he does too. The textbook we used 2 years ago went through the quantum mechanics of the oscillation of the neutrinos. Here he talks about why we expected something like that and how we saw it, but that won't be as part of the test. But it is something very important with the number of detectors around. They did some detect electron neutrinos, some detect mu meson neutrinos, and so they can look for these effects. And then we've got the conservation laws. Remember, these are conservation laws that happen some of the time. They have qualifiers with them. And then the strange particles and what that means, and how we got to classify them that way. So a little bit of the history there. And then we talked about resonance particles being those things that have such a short lifetime that you can't see that anything is moved in the bubble chamber, but you can because of the uniqueness of the momentum of the particles coming off. Then there was just some discussion about how the kinematics of these things work, how you can work it out. It's very reasonable for me to give you an equation, an interaction on the test, and ask you what are the energies of the particles or the masses of the particles or something, given certain bits of information about the collision. And so you've got to pull out your relativistic energy terms and your relativistic momentum terms and work through it. You don't need the coordinate transforms, but we'll have it all done in the center of mass so that things are a little easier to deal with. Mm-hmm. And they talk about what's the threshold kinetic energy. That's always the lowest kinetic energy for which Q of the reactions, these are just like the nuclear reactions, which the Q of the reaction is 0. That is, in the center of mass, the collision takes place and all the products that are produced don't move anywhere. Then they talk about the eightfold way and families, and we didn't really talk about those much. It's important, but we weren't going to do anything with it. So we went from there to quarks, and then with the quarks we did a little bit about the color and Feynman diagrams. We talked around the Standard Model without talking about it directly, and we did not talk about the Higgs boson. But there is a fascinating book that one semester the SPS group met once a week, and we read this book called Massive, which is a sort of a history of elementary particle physics, and puts more words behind what this chapter has in it to give you an idea of what the Higgs boson was searching for and why. And at the end of we finished the book, and 4 months later they discovered the Higgs boson. So
that's pretty cool.
Yeah, so they released the book
Good timing.
An appendix that discussed what happened in the discovery. So the book is called Massive, and it's a very nice read. It's not it's not a hard read, but it's not easy. And when we were doing it, one of our alums was at CERN working on his PhD and ended up being there for the announcement of the discovery. So he was filling in all kinds of stuff in different parts of the book. All right, so those are the things we'll cover, and I thought we could do 3 things. One is to look at conservation laws. One is to look at Feynman diagrams. And then we'll do one collision where we have to do the energy and stuff. How does that sound?
Like that.
Sounds good.
Okay. So why don't we start with some problems.
After 3 minutes to wait on the food, I'm going to give you your plate. Mac, are you coming downstairs, see?
Let me see if I've got my, here we go. Okay, so I'm going to go to the whiteboard for a minute. And if you've got your textbook there, you want to turn in it to the
Tables.
the tables. What pages is this, Chip? Page
Like
5.
70 something.
And I'm going to.
When did they come out with their discovery of the Higgs boson?
Oh yeah, it's 574 page.
What year? Was 2011, 2012?
Oh wow.
Maybe somebody can Google that real quick and tell us. Let's see here.
Let's see, they got the Nobel Prize in 2013.
So let's get 2012. Yeah, because it was the.
Apparently, it has the nickname the God particle.
That was Leon Letterman, and he paid quite a price for saying that, and it was his publisher who insisted that he title his book that way, or so he told me.
How was everyone's day?
Unproductive.
Unproductive?
Very unproductive. Yeah.
Is there any way to keep the Zoom from taking over your whole screen?
I just have my.
I just.
Like you click the box up in the top right, and I pulled it right next to like the chart behind it.
Yeah, I don't have anything that it's letting me think of.
I just click on it and then press the escape button, and it usually makes it smaller.
Ah, there you go. Okay, good. All right, so the question is, which of these things can happen? So I've got, I think we did one of these in class the other day, but all right. Can this happen or can it not happen? If it can't happen, tell me why.
I'm assuming it can't happen because the charge wouldn't be conserved.
Wait, there are no charges.
Is this, is the, you know what letter is this?
Wait, hold on. I have the wrong chart. Hold up.
Is that what in that? It's a neutral.
I don't think that's in the. Oh, just kidding.
So this particle is, what's this letter right here?
It's a sigma.
Sigma.
Sigma,
What's this letter right here?
lambda.
No.
It's gamma.
It's lambda.
Lowercase gamma is this.
Oh.
All right. Can this happen? So charge is conserved. Is this mass of the sigma bigger than the mass of the lambda?
So
Yeah, I think.
so
that
if
can
you
happen.
have particle, like if the sigma was less massive than the gamma, would this still be possible? Like, can we write it this way?
The mass of the lambda was bigger than the mass of the sigma.
Yes. Can we still like write it this way?
No way that can happen.
Sorry.
No way this can happen.
All right, I see. Yeah. So this is just like decay, right? Like you are not
Yeah, just
providing any energy.
right. Which case is true here? And how's the other masses over here?
The sigma is larger than the lambda.
Okay, so then that works. It's energetically possible. What else can you use to make a decision here? Any quantum things we can bring to bear?
Well, because there's a telescope.
How about baryon? Baryon number?
Baryons are good. Baryon numbers are good. They're the same.
So is the strangeness number?
The strange number is the same too. Yeah.
Strangeness number works.
Yes. Oops.
And the lepton numbers work.
That's all the information they give us in that table, isn't it?
Yeah.
All it looks like all
Yes.
the other are going to work. Okay. So you let me get away with something here. What's the mass of the sigma?
1189.4. MeV?
Well, a lot of them.
No, it's 1,192.5. Boy,
Oh, sorry. Yeah,
1,000.
it's actually
192.5 MeV.
I see.
What,
oh, I was on to something.
So the
I
mass-
guess if you added the mass
Mass
at the
is
beginning of
fine.
the decay is less than the mass at the end of the decay. Because if you add the pi to the sigma, it's more than the sorry. If you add the pi to the gamma, it's more than the sigma.
well, this won't work because of the energetics, will it?
Well,
Why couldn't they have some energy and make that happen?
how can we know if the energy can be lower than the speed of light?
You can't have
Because you can't create energy.
We can
I
accelerate
see.
that with the speed
if this
of...
was colliding with something, you could add energy. This is just
Oh,
sitting there.
Okay.
So that can't work because of conservation of energy. All right. Let's go to the next possibility. Here is a delta plus goes to a proton plus a neutral pion. Charge conservation work?
Yes.
How about energy conservation? Mass energy.
Uh,
It,
Yeah, it will work.
it works.
Yep. That'll work.
Yep.
Baryon number?
This wouldn't work.
No.
No, actually it will work. Yeah, sorry.
Actually,
No,
it
no,
works.
will work.
Yeah. They're both...
Yeah,
This is baryon
one
number.
and one.
Yes, plus one and plus one. Okay. How about lepton numbers? Those work?
Yeah.
Yeah, both zero.
They're all zero, right?
Yeah.
What about strangeness?
uh,
0 and...
Yeah, all zero.
Okay, so this one's a possibility then, isn't it?
yeah.
So this is a weak interaction, right? Weak force, weak nuclear force, right?
We'll take a look at it and see.
Yeah, I'm just. Yeah, I mean it's a decay, so I assume it's weak. I'm just making sure I got it right.
All right. So here I've got pi plus, decay to V plus, and a gamma. Charge conservation,
Conserved.
mass energy.
Oh.
Oh my God, leave me alone.
Just mute.
Works, does it? Pi meson's bigger than
Oh,
meson.
but she was not his hers. That was Bill's thing.
Yes.
Where can I find the gamma?
Go
Uh,
for
no.
it.
A gamma is a photon and it has any energy that it needs.
I'll move out of my house. I want to see my friends back. Back.
Sorry, I couldn't hear because...
Where did
can
you say the
make your-
gamma was?
It's anything you want it to be.
Okay.
Oh,
Or that
Yeah,
that
then it
needs
should
to
work,
be.
I guess.
All right. How about baryon number? None of them are baryons, are they?
Yeah.
How about lepton number?
Yeah.
Zeros.
Yeah. The muon has a lepton number.
They don't have lepton numbers.
Well, they have
The muon has a lepton number.
yeah, it's lepton muon number.
Ah,
On the chart, with the lepton number, is that the L?
Yeah, there's like Le, which is like lepton.
Well, it has a lepton muon number because it's a muon.
Oh, okay. I was just reading the chart wrong.
so there's our
Boy, can't happen.
Can't have.
violate lepton number.
The only problem with telling this story is that I felt like I only did it. I felt
Oh,
like
yeah.
I told the story first, it would have not even like the only reason why.
All right. Here's the problem. K minus goes to pi minus plus 5 is equal to. So each of you do. I'll give you a couple minutes. Let's see what you got. Okay, I'll close with everybody.
It doesn't work because of the strangeness number.
Anybody else agree with that?
Yeah, the kaon has a strangeness of +1.
That. So since all the other quantum numbers are conserved, you can violate strangeness conservation with the weak force interaction.
So it can happen.
Can happen. All right, let's move on to a variation of this. Get a little more challenging here. Got a collision in this one, so we can bring energy. So that mass energy can be consumed. How about that?
Violates charge, right?
Protons plus.
Plus.
So is it, we have charge conservation.
Yeah.
Oh, yeah, it does.
Okay. And as long as we bring enough energy, it can happen. So let's go through the other rules. Baryon conservation.
baryons conserved.
Baryon number in the picture is, oops. That's interesting. Baryon number is equal to 1 on the left side.
Yep.
On the pi mesons, baryons,
No.
It's just 1 and 1, so they're conserved.
What about lepton numbers?
They're conserved.
On the left,
0 and then 0.
on the right, they're all pions, so zeros. Strangeness?
Let's see.
It's 1 and
+1 on the left.
it's 1 and +1 and -1.
Is it a K minus? Yeah, it's a K minus, so it's -1, isn't it?
Where is it?
And what about the sigma?
-1.
-1. That's it. It can happen, can't it?
Dr.
No,
B, I have a
that'd be
question.
the K minus has +1 strange number and sigma has
For
minus.
math, for the K minus, and then you had the pi minus and the pi naught, would you the energy of each side and see if they equal each other? Like, how does that work exactly?
You add energy to the incoming projectile.
Okay,
Actually, it's probably this.
because the K minus is 493.7, and then the pi minus was 139.6, and then the pi naught was 135.
Yeah, there's a lot more mass on this side, isn't there?
Yes, or no, I was talking about the previous one that you had, but say, like, the numbers don't exactly equal each other, how does that work? So if one side's less than the other, then it is conserved?
Okay, so this can't move.
Yeah.
We put ourselves in its center of mass framework, it's not moving. So it's got to have more mass than this side, because when this decays, these will also have some kinetic energy. So if this mass isn't bigger, if the K minus mass is not bigger than the two masses on the other side, then your Q for the reaction is less than 0.
Okay.
This is a less than instead of a greater than. And a negative Q means you've got to bring energy into the collision. And we can't in this case. But now, up here in this case, even though the mass of the right side is bigger than the mass of the left side, I think. Isn't that true?
Yes, that is true.
But we can always just add more kinetic energy to the K minus coming in, so that when it hits a proton, it has enough mass energy to make all these things.
Okay.
How do we?
So basically,
Go ahead. Sorry.
if the right side is less than the left side, then the energy or mass energy would be conserved, right?
So think of this as the same way we did when we were doing the nuclear reactions. We had a a decay or we might have a neutron plus uranium 235 goes to two isotopes. And usually these are formal neutrons, so there's no kinetic energy. So the mass on this side has to be bigger than the mass on that side, so that the sum of all the kinetic energies, that is the kinetic energies of the products minus what you start with, is greater than zero, or can't happen.
Gotcha. That explains it. Thank you.
Dr. P, is there a way we can just estimate the maximum kinetic energy they can have? Because they cannot go faster than the light.
Oh, yeah, but remember, let me put this in here. Remember this. So this energy is the square root of p squared plus c squared plus a squared.
Yes, sir.
That's the total energy, right? That's equal to the mass energy plus the kinetic energy. So gamma can go to infinity. So you'll never have a particle that has to move faster or even equal to the speed of light. So you can get from the speed whatever you want. Now at CERN, I believe their gamma is 0.9999997 or something like that. That's pretty fast.
Wouldn't that be faster than the light because of the air?
Yeah, boy.
The gamma. Theta.
That's what vacuum chambers are for, Minju.
So they're faster than the light we're seeing right now.
I'm sorry, what did you say?
I was just saying they could be faster than the light on the Earth.
You know, when you get fast enough, the index of refraction of the air in the atmosphere slows down regular light, so human can go faster than the speed of light. So that's how we get energy particles coming into our atmosphere. They produce a type of shock wave, of light shock wave. It comes in and has a particular wavelength, and that's the particles exceeding the local speed of light in the atmosphere. It's called Cherenkov radiation. And
Is that the one same as the thing on the Iron Man's chest?
you got me. Oh, no. Okay. As best as my calculator can do, gamma is 408 here. So that means if you had a photon, its energy coming in would be 382.7 something much MeV. No, it's going to be GeV.
Better than possible.
GeVs. So maybe they don't have that many nights. Maybe they've only got that many. I take that back. Yeah, they can go to 10. CERN goes to 10,000 GeV. So yeah, so maybe it's this. That's what it is. So the point being that you can get whatever energy you need. Velocity-wise, you're not changing the velocity very much, but energy-wise, the amount of energy that these particles acquire is extraordinarily large. And when it comes to momentum, and momentum is what the magnets have to interact with. So you change the energy of these particles too much, you have to build new magnets and kind of higher magnetic fields. And we've kind of run out of our ability to do that. So the next accelerator will be probably 4 times the diameter of the present one. It'll take more magnets, but they bend it less. That's why we have to have a bigger radius. And at some point, we'll put it all into outer space so we can use some gravitational field of some planet to keep the things in orbit, but keep it out of their atmosphere. I want that job. All right. So is everybody happy with that?
I'm following. I like it.
All right. Let's move on.
Andrew, is someone getting murdered in your kitchen?
I'm at Sam's house. They're watching a movie.
Oh, spam.
Yeah. I will.
I said,
Damn. Is that Professor's doing?
Allah, I haven't seen your face in days, bro. Where did you go? I miss you.
I'm here. I'm just. I don't know, and I don't see why should I open the video. You know?
What is the Fed watching? Is that what it is?
Sorry.
Are the Feds watching? Is that why you want to turn your camera on?
I don't know, man. Maybe I don't know. You know, don't know who's watching these days. You know.
I understand, man.
All right. Lepton.
dude, I don't think I've seen Hank since we left.
I've heard from him. Okay, lepton number. Is it conserved in this one?
What time? Oh, I gotta pull up this chart.
So what is this last term? Is it like a photon?
It's a neutrino.
Yeah.
It's not conserved. We have plus 1 on the
Electron neutrino?
Yeah.
Yeah, so the lepton numbers are equal to
1.
0 to minus 1.
0, 0, and then plus 1. Oh wait, minus 1.
Yeah, minus 1.
And then
whatever.
Oh, I guess +1, so they are conserved.
Yes, +1 for the neutrino. The anti-neutrino is 1. And the E plus is considered the antiparticle here. Okay, let me find another one here. The lepton numbers.
It's conserved.
Yeah, so the electron neutrino is a +1.
Yeah.
Electrons is 0, neutrons is 0. And the positron is
+1. No, sorry. Yeah, +1. Or -1? Because it's +1. -1, sorry.
Oh, +1.
positron is -1. The neutrino.
-1. Oh, maybe.
So this doesn't work.
Oh, yeah. No. Don't think so.
Okay, so we've got mu lepton numbers, and what's the mu lepton number for a mu minus? Isn't that +1?
+1. Yeah.
Electron is 0. Electron neutrino is 0. And the muon's neutrino is a +1, isn't it?
Yes.
So it works for the muons. Now let's check the lepton number for electrons. Muon has 0. The electron has +1. What of the antineutrino? Isn't that a -1 for an electron?
Yes.
The anti-neutrino.
So it works.
It's -1. Yeah.
I wouldn't think this would be hard, but the variation, where you put them, which side gets you. All right, we'll try something here with strangeness conversion. So I've got an omega
When you're doing one, it doesn't matter what lepton it is. Like, it doesn't matter if it's like the lepton muon number or like lepton electron. It just matters like what side, correct?
Yes, which side it's on.
All right, that's what I thought.
Just like the nuclear reactions, just like chemistry too.
Okay.
All right. So what's the strangest number of an omega minus?
-3.
-3. Really?
Yep.
What's the quark content of an omega minus?
Wait, could you repeat the question?
The quark.
The quark content of an omega minus. Really quark tables.
That one's on like 60 something. Well, let me get to it. 174.
Yeah, 575, 574.
Yeah.
What's the omega minus quark content?
Is it red, green, blue?
Three
Strange.
Red, green,
three stranges.
What's the strangeness number for an S quark?
-1.
-1. There's 3 of them.
Oh, yeah.
Okay.
Wow.
What's the strangeness number for an anti-S quark?
+1.
Yeah. All right. So what's the strangeness for a lambda? By the way, is this a lambda 0? Yeah, this is a lambda 0, isn't it?
Wait, why did you write down the anti-strange?
Just to make you think.
Yeah.
It's not part of the solution.
It's -1.
-1.
So it's -1 and -1. So it's strangeness.
No.
No. Is the omega minus mass greater than the sum of the 2 masses on the right-hand side?
Yeah.
So, if we are allowed to violate the strangeness conservation one, like for the weak interaction.
The K-on is 493.7. Yeah.
This is possible mass energy. And it charge is conserved. The only thing we're violating is strangeness number. Right?
So it works.
And it's only 1 unit, so this could happen as a weak interaction.
So are we? So if it's more than 1 unit, can it still happen, or we are limited?
Well, we'll explore that idea. No, we won't. I think the answer to that is no. I don't think it will happen. Sigma 0 goes to a lambda plus a gamma. So mass energy wise, it works.
Yes.
Strange.
Charge is conserved. Baryon numbers conserved.
Bless you.
Bless you.
Bless you.
Let's see.
So
Dr. P.
-1 and -1.
So the gamma particles, when you said it can be anything that you want it to be, could you go into detail about that?
The photon. So these other particles have defined rest mass energies, and their energies can't go underneath that out. The gamma will have whatever energy is left over from the interaction. So it'll just be whatever we want it to be.
Okay, thank you.
Now, so for that reason, a gamma is it's one of the force particles, but it doesn't change strangeness or any of these other quantum numbers. But the fact that this can happen and you've got a gamma there means it's electromagnetic. Interaction. So it's like an excited state of a nucleus and emitting a gamma. You don't usually say that the element changed when you did that, but the mass of it changes. And here we give particles with different masses different names.
Awesome. That makes sense.
All right, last one here. Let's have a lambda decay to a proton and a negative pi meson. No problem with mass energy conservation, so no problem with baryon numbers, one on the left, one on the right. No lepton numbers come into play, so it's just the strangeness here. What's the strangeness of the lambda?
-1.
Yeah. What's the strangeness of a proton?
0.
0. Pi meson?
0.
So delta
0.
equals 1, so this will be by the weak interaction.
Is that the only way we can know that it's a weak interaction?
You faded out on me. What did you say?
Is that the only way we can figure out if it's like a weak interaction?
Good point, yes. All right, let's make this a little more challenging. Same thing, but all the conservation laws are in effect here.
Oh God.
Proton collides with an antiproton. That's what they do at CERN. They have
In the strong force interaction, all the conservation laws are conserved, right?
yes.
Right.
All right. Does that happen?
Yeah.
Fortunately, for you, the pion has an incredibly bland set of quantum numbers, doesn't it?
I think that works.
Works. Everything's obeyed, isn't it? Goes by the strong force. Take an electron neutrino colliding with a proton, not an antiproton. And it's going to go to positron, lambda, and a kaon. K-meson. And I know there's two K zeros over there, but they all have the same
Want
quantum
some
number.
extra turkey on it? Okay.
What did it not work because mass energy?
We can bring in any energy we need from the neutrino.
Oh yeah, I forgot. Yeah,
Except
forgot that it was a collision on that left side.
all the quantum numbers work.
Except can I use this number? It doesn't work.
But what doesn't?
Like in the strangeness number, it's like the left hand side is like 0, the right hand side is -2. Like I'm missing something.
Wait, K. No, I think the right hand side, because that K on is +1.
Is it +1?
Yeah.
Yes, yeah, I didn't see this yet. Thank you. Yeah, I guess it works. Yeah.
How about the electron lepton number?
It's conserved.
Well, it's -1 for the positron.
It's not.
Does not. Doesn't happen. Let's try this one. This is a neutral. Mass energy works. Charge works. Baryon number works. How about the lepton? Electron lepton 0 0 goes to -1 0.
Doesn't work.
Lepton mu lepton number -1 0 goes to 0 plus 0. It doesn't work for that reason either. Well, that one's forbidden. All right. Let's start looking at quarks a little bit. I've got a lambda going to a proton plus a pi 0. What's the quark composition for lambda? Well, that's what, page 565? You have lambda 0 in there? Yes, they do. UDS. With the proton.
Hmm. The pie's not on there for the pion's not on there for us.
On there. You know, I emailed those readings for you on Tuesday, and one of those sheets was a collection of different tables. Can you pop that up and take a look at it?
From the say again, from the PowerPoint.
Well, let's see. Hang on.
The title's like too much modern physics reading or something.
No, it's not that one. It's a shorter version of that.
Like the quarks and particle compositions?
Yeah, that's it.
Are we looking for the proton?
Looking for the pi zero.
Oh, the pi zero. Let's see. Oh shoot. Pi minus and pi plus. Oh, the pi zero. U anti-U.
U anti-U?
Yes. There's also another one for it. It's D anti-D. It has a comma in between the two. What exactly does that mean?
That means that they're actually added together and you multiply by the square root of 2. One
Okay.
of 2. And for us, we could use the or. This is more of a technical thing. When it can be both, you have a linear combination of the two. So, how does that work? We've got an S quark over here, and we don't have an S quark over here. So somehow, when we start off with a U and a D quark, we're probably going to keep them, but the S quark, something's got to happen to it. So we can have the, let's see, I'm just going to show them going straight across here. Okay, so we're doing Feynman diagrams right now.
Mm-hmm.
And the U and the D, so what I need is a D is to get, or no, another U, so that this would become a proton. And that means I also need an inverse U. To produce a U bar pair.
So like whenever we have quarks changing, this has to be a strong interaction, right?
Well, it can't be because the strangeness number is not conserved.
So if we have a situation where everything is conserved, how can we tell if it's weak or strong?
It's usually considered to be strong when you say that.
So just it's called strong. Does it have something to do with like how much force is carried, or because everything is conserved?
It means you don't have to have a W involved in the interaction. Got it working on that one. Okay, so I can do this. So
They're pretty. Yeah. I'll finish them tomorrow. I only did one.
all right, I'm going to switch us back for a minute to show you this.
Are there any longer left?
5.
All right. By the way, here's the new periodic table, right? These are all the very elemental stuff. Here are your quarks, here are your leptons, here are your force particles. And
Tomorrow I'm going to do the pink color on her.
so, see this interaction here, how a U and a D bar can annihilate and produce a W plus. And then the W plus can spawn off a particle-antiparticle pair. But it can spawn off two quarks, one quark and an antiquark, or an antiquark and a quark can create one. And if it doesn't decay to quark-antiquark, it goes to leptons in the same family. So you've got a conserved lepton number in this process, so they'd have to be mused. So here's all the examples of what a W plus, a W minus, and a Z particle can do. And so they say U and D here, but they show one as a particle. They show these both as particles, don't they? But if I rotate it counterclockwise, so let's remember this, the U goes in and comes out of D with the W plus coming off. Now, can you take that and rotate it counterclockwise 90 degrees and tell me what you've got?
It would have been the same as that first diagram, right?
Kind of.
If they would,
Be very careful when you rotate it to keep all the directions of the arrow the same.
oh wait, yeah, never mind. Because the D would be coming in.
So when we rotate it, the D is actually an antiparticle, isn't it?
Mm-hmm.
Because its arrow is pointed backwards. But the way they've drawn it there, they're both regular quark particles. So depending upon how you rotate these things determines whether they're particles or antiparticles. And you notice with the W particle, the U can be on either side, and so same with the D, and it comes in and it goes out when it's up. And the W minus does the same thing with the charm and the strange. And then the Z, it works with the, I can't read that well. Get the book I get out of. So the Z goes from a lepton to a lepton, and that'll be a lepton particle to a lepton particle. The W minus can go from a lepton neutrino to a lepton particle, and a W minus can also go from a lepton particle to a lepton neutrino. So that's what that means at the top there. So the Z goes from neutrino to neutrino or particle to particle, and the W's can bridge between the two. So now that you've got that in your head, let's go back and put it to work. Oh man, it erased it all.
We had a lambda on the left side,
That was a lambda.
and then a proton and a pion.
Okay, so we had the U, D, and S going off. We know we've got to create another U to make the proton. And we've got to, it's springtime. There's an ant crawling across my tablet here. We've got to turn that S into a UU bar somehow. How are we going to do that?
With a W somehow.
Okay, so the W plus will take a W minus will take a strange quark and turn it into a charm quark. I don't know what that does for us.
Oh yeah, I actually have a really important question.
Yeah.
What time and day is this exam?
2:00 on Saturday.
Okay, perfect. Thank you.
Guys, I thought I had this one worked out, but I don't remember how I did it. We'll go on because, but somehow we've got to take this book and it will come in. Let me have to go down this way. It can become a sequence with the W minus. No, I'm just thinking about this. Well, this should work.
It's a tough one.
Omega is energy is conserved in this one, right? The omega. Yeah. Lambda A or less than the omega. Just barely. Yes.
So how do we know when it like to turn that S, I guess, into the anti-U? Like, where does that C and W minus come along? What can we refer to know that?
You would have to have these branching.
Okay.
So there's nothing obvious about this.
Okay.
Okay. So I was thinking we were limited, but these are just particles here. So as long as any two can come off, so it doesn't have to be the C here. So this could be a U. And that would be the U I need up here. Now the W minus can come down. By the way, is the W minus right here? What's the S charge?
The S charge is minus 1/3.
Minus a third. Yep.
Okay.
Minus 1/3.
U charge. The plus a third?
U charge is plus 2/3.
Plus 2/3. And so the change in the W has to be a minus then, doesn't it? Okay, that's a W minus. And then I'm going to have the W minus come over here. And sorry about that. We would like you to do that in these drawings, but they finish them up. And then I'll have this, and I've got a W minus going to the right. And then this has to be this way, and this has to be this way. That's the rule for the W minus. And that will be correct. There we go. We got it.
Dang.
So the only rule on this is whether you need a W plus or a W minus depends upon the charge of the quarks before and after. And what's on the left, and they showed that branch with the W minus going down, and that's what the charm was coming in and the strange was going out. When we switched it, W was going in and the strange quark was going in and out like that. So I can rotate these. And so this one right here, if I took out the C and put in a U, which I can do because I conserve charge when I do that, and then I rotate it this way a little bit. Oh, wrong direction.
So does that work with any quark that conserves charge? You can basically just switch them out.
Yeah, as long as the charge works.
Okay.
You have to be careful.
So what about so down there, the W minus obviously has the charge has that minus 1/3. But how does that play into like the anti-up and the up for that pion?
The W turns itself into a quark and anti-quark, which is what we need. So this is a W minus. So let's check it and make sure we haven't made a mistake here. So W minus comes in with -1 charge. What's the charge? Well, this won't work, will it? It won't work because these are.
Yeah, that's what I was kind of confused by.
So we're not done yet. So we can have a U bar there and another quark here. And it won't be an antiparticle, right? So we can make a D out of it, for instance.
No, go to bed. I'm already downstairs.
I have to go. Dr. P, thank you very much. Appreciate it.
Yeah.
For one and a half.
I'll give you
Yes,
the
I promise you 100 on the exam.
Good.
Bye.
All right, Seal.
See you
I
for
expect nothing less. Hey, Andrew. Oh, ah. So why does that W have a charge of -1 right there?
Well, it can't change its charge, right? It's just, it was -1 up here.
Ah, okay.
Maybe what I want is, what's the charge on a D?
-1/3.
-1/3. And an S is this.
Oh.
So this would have to be a Z0 here. Oh, what do we need for the proton is a UUT, right? This has to be. Well, anyway, I'll go look for my notes on this one and help you out.
We'll have to come back to this one.
So you see the kind of game that gets played here
Yeah.
with these things. Let's try this one. Pi minus plus a proton goes to a neutron plus a pi zero. So what are the what's the quark composition here for the pi minus?
The pi minus has quarks anti up and down.
And so the proton is a
UUD.
UUD. The neutron is a DUD. And the
Yeah.
pi minus is the UU bar, or a DD bar, whichever. Okay, so if we have the pi minus here, Yeah. Proton here. And I go along. This one's pretty easy. These three make a neutron, and these two recombine and make pi zero.
DDU.
And since there's no W involved in this, it looks like this is a strong interaction. Every baryon number is conserved, everything's conserved here. So this is a strong interaction. All right, that one's pretty easy. So let's take the case of the sigma plus decaying to a proton and a pi zero. So proton is a UUD, pi zero is a UUR. What's the sigma plus?
UUS.
Okay, so a U and a U, we're going to go to a U and a U on the proton. The S has got to change itself. We need to end up with a D and two U's. So let the shorten this here. Okay, here comes and I'm going to, okay, so I'm going to show the W and have a U come on, or yeah, I'm going to have a U come off, and the W is going to be what kind of interaction here? Goes in, goes out. What's the charge change on it?
The charge would be -1, right?
What's the charge on the S quark?
-1/3.
-1/3, and the U quark is
And U is +2/3.
plus 2/3. So the W minus, doesn't it?
Yes.
And I believe that it goes like this. Okay, so now that just tip it a little bit to make it more like we know which way time is moving. So this will be a W minus moving here. And then I want it to turn back into a U
You need
bar.
a D.
If we have so if it's coming this way, This one has to point in here. This one has to point out here. So this would be the antiparticle, so that would be a U bar, and this would be a D. Does that work charge-wise? What's the U bar is minus 2/3, right?
Yeah. Yes, minus 2/3.
D is
And then a D. D is minus 1/3.
minus 1/3. So that's -1, and that's a -1. That works. So I'm going to, oops. I'm going to take this up here. That's my D. And that'll be a proton, or a neutron, proton,
Yes.
UD. And I'm going to take this U down here with the U bar, and that's my pi 0. So you can use any quarks you want as long as the charge is conserved and as long as you keep these arrows going in the direction they're supposed to belong. So like this. If I turn that upside down, that would, so if I rotate, right, this one would be pointing out, this one would be pointing in. So here you have a particle coming in, a particle going out, and a W. Here you've got an antiparticle going out. So it's possible to do a number of things with them. You have to remember things can't go backwards in time. All right. That gives you a flavor of those things. Let me just do something real quick here. Suppose I wanted to produce from a collision of 2 protons. So I want to do that. Is the number conserved here? This is an easy one.
No. Oh, wait, yeah. Yes, yes.
Okay. Lepton numbers, they don't have any lepton numbers. They don't have strangeness. How about charge conservation?
Plus.
Conserved.
Yeah, that works.
But wouldn't you need like a huge amount of energy to make this happen, right?
Exactly. But this is how the antiproton was discovered. This is how we make antiprotons, to make beams of them. So when you get to CERN, there's not one accelerator, there's a whole bunch of accelerators. So, what energy does it take? We're going to assume this thing sits still. It's the target in the bubble chamber. Proton comes in and hits it, and it turns itself four particles. But they all just sit there. So what you see is a proton coming in and disappearing. Energy has to be conserved. Momentum has to be conserved. So we checked all the other quantum numbers, so this is all that's left. What's the energy? Let's call this particle 1, 2, 3, 4, 5, and 6. Now, in all of these collisions, where you want the minimum kinetic energy for the incoming particles, just make them happen. What are these particles doing? So let's go to the center of mass. Here it's really kind of nice. Two protons are coming in with equal speeds in the center of mass. When they collide, all the energy in the center of mass creates three protons and an antiproton. And they just sit there. Now, that's what really happens whatever that velocity is. If I add that to every particle in the system, then we would have the initial proton hitting this particle at rest, and then after the collision, four particles are bunched together, moving at this center of mass velocity. So in this collision, when it's all done, four particles act independent of each other, but they all have exactly the same momentum. We'll be moving to the right. So the momentum conservation is the momentum of number one. Number two is at rest. It's got to equal to 4 times the momentum of the product. So let me just say the momentum of number 6 is the example. Those two momenta have to be equal. And since they're moving in the x direction, we could just say the x and remove the arrows. We'll just be dealing with the magnitudes. Now, what about energy conservation? What do you put on the left-hand side? There's for particle 2. What do we put for particle 1?
Square root p squared c squared plus m squared c4, c to the fourth.
So this is your mass energy before, and you want it to the mass energy after. It's just 4 particles, each with the same momentum, each with the same mass, and then it's plus q, but we want q to be 0. We want it just barely to happen. Now you can solve these two. And the easiest way to solve those, if you don't want to do it algebraically, is to use Excel and go. How many unknowns do you have here?
Just
Um,
Just one.
momentum, right?
Well, since you know the incoming energy of the projectile, you know it's so you know that.
Here has energy.
The only thing you don't know is this one. This is a little easier. You can solve for a piece of x and put it in there. Oh, you know, basically. And that'll let you solve for Q, and that's the total kinetic energy of these particles, because we put all the kinetic energy on the other side. Look at this.
So would we have to use goal seek to do this one, you think?
Yeah, okay, so here's the reason you have to use goal seek. I'm just trying to remind myself why you have to. You've got MP plus the square root of M1x squared p squared. Is equal to 4 times the square root of p1x squared c squared over 16 plus m c to the fourth. Okay.
Whoa. Wait, why is it over 16?
Because this momentum is equal to 1/4 of the incoming momentum, P1x. So I changed from P6. That means I've got one up
Okay, that makes sense.
which I solved for, but in fact, the algebra gets very messy. So you could just go to goals and say, look, calculate 3 things and subtract. You have an equation where you have all of that energy minus that energy. And you'll have a cell with P1x. So you'll say, set this cell equal to 0 by changing that number. And so it'll just change it
By
until
changing the first number?
it's changing the momentum, the thing you don't know. So it'll change it until the energy is equal to the energy after. All right, so one cell, you put equals the energy before minus the energy. And you put in all the values you know except P, refer to P in the cell above. And then goal seek, you say set this equal to 0 by changing this. All right?
Wait, so I'm sorry, set what equal to 0?
You set
You would set just the left side equal to 0.
you take this whole equation. This is the energy before, and this is the energy after, and you take the difference. When they're equal, then their difference will be 0. but you can put that in.
Hmm.
So you put equals the energy before minus the energy after, where the energy is being calculated using this momentum right here. And you don't know it, you just put something in there and let it be a placeholder. And this won't be equal to 0 when you do it. But then you go to goal seek and say, hey, make this 0 by changing this number right here. And it'll do it. And so when you're done, the left side equals the right side, and you know what momentum it took to do that. Another example. What's x equal to? Well, algebraically, there's no way to solve that. So create a cell where you say x is in this cell, and this cell is x minus e to the x. And then you use goal seek. To set this cell equal to 0 by changing the value in this cell. And that cell can only have a number. It can't have an equation. It's got to have a number in it. It's got to be, this one said equals previous cell minus exponent of previous. And so it just starts iterating. Puts 1x in, it goes down and calculates this, checks it. If it's not 0, it goes back and it changes this again.
So in the other one, we would basically just have to have the momentum of
We have the
basically just px1 and it's in a cell by itself, right?
squared plus p1x squared c squared plus m squared c to the 4 minus 4 p1x squared p squared over 16. It's all under the square root. Plus m squared c. And then this cell that you're going to try to solve for, you've got the p1x value. So when you enter these equations, you know MC, you put it in, plus the square root, you go down to this cell and get px divided by squared, plus, and you know MC squared, put it in, then minus 4 times square root, gets p1x there, times c squared over 6 plus m 4. And you can do this. Algebraically, you could do this. It'll take half a sheet of paper and some careful notation. Or you could just go to goal seek and get the answer. So goal seek for problems that look like this, that cannot be solved out. Okay? Where it's meant for algebraic problems like this, you don't want to bother to solve algebra. You can try this one.
I think I've only used goal seek like twice. And they were both this semester.
Try a couple variations of this. Well, actually, I think this one will be fine. Try this one, then try this.
Alrighty.
I want to think the answer to this one is 8 MeV, 8,000 MeV, something on that order. Didn't need to do that.
Jeez.
Something like that. Take the square root of it, it's the energy is 8 MeV. This should be, yeah, that's right. Give it a shot. See what you get. So I'm going to try that Feynman diagram that we got stuck on, and I'll send you my answers to these two problems. So you can give
Awesome.
your effort too. And I've got this recorded, and it'll be on the Dropbox thing in about 15 minutes. So if you want to come back and look at these problems, you can.
Okay.
All right?
Sounds good.
All right, guys. Good night. Get some sleep.
Thank you very much,
Thank
Dr.
you.
D.
Dr. Peterson, do you have a minute?
Yeah, I do.
Thank you. About the paper, you said we have to solve a problem or two about our topic, right?
Yeah, I was about to ask that exact same question,
So what
like
is
word
your
for
topic,
word.
Law?
Sorry?
Well, what is your topic?
It was Raman spectroscopy, and I don't think the book.
Raman. Okay, so I started looking and I just ran out of time today. What's yours, Will?
Well, I started writing on radiation damage and matter, like specifically in like biological matter, and I realized that there's not really like very many good problems on that.
Well, I can find a couple for you.
Okay. I mean, there are like the book does have some problems on it, but it's mostly in the sense that like it'll say like, you know, like one of them's assume an X-ray technician takes an average of 8 X-rays per day and receives a dose of so and so. As a result, like estimate the dose per X-ray taken, like stuff that are just not very informative questions.
Yeah, I know. And I can get a little bit better than that, but they do stay a little, they can get extremely difficult or they look like they're trivial. There's
Yeah.
a
Well, all the ones in the book are like pretty trivial, like can be solved in like 2 lines,
yeah,
basically.
So let's see, I never took the licensing exam, but I was qualified to be a health physicist. So
Interesting.
I've done a little bit, and I've taught once a course in health physics. So I'll look something up.
Okay. Well, I was really trying to find something like a problem that had to do with like ionization effects in cells, but I just could not find anything. It was all kind of just broad, like stuff that I couldn't really use in a paper very well. So anything that you could find would be helpful.
For the last 15 years, we've been able to look at the effects on individual cells because we had them and kept them alive, and looked at the effects of one neutron or one alpha particle interacting with them. So, yeah. How about you, Minju? How's your paper?
I think I'm gonna do the superconductivity, but focused on the superconducting quantum interference device.
Squids, okay.
Yeah. So probably I should
Andrew told
calculate.
me he's done with his.
I just started. So probably I should calculate like tunneling in Josephson Junction.
Things like tunneling and that are good. And you'll have an energy gap that you can deal with that allows you to predict what these are. I'll see if I find something that's particularly interesting.
Okay. If you can
I'm sure you
find
found.
something related to magnetic monopole or like dark matter detection, that's what I want to write about.
That's a little tougher. That stuff gets pretty challenging pretty quickly. But squids are.
I don't even know what dark matter is.
Yeah, well, that's part of the problem. We don't know what it is. Lots of ideas that might be, but we don't know. All right, guys. You'll have a good night.
You too.
You too.
If you could maybe
Maybe.
help me find some stuff on that, it'd be very helpful.
Thank you, pancakes.
Right?
This is
Pancakes
Yeah, my dad made me some pancakes.
at 11 p.m.
Oh, now? All right.
isn't this a football thing?
Blueberry or just regular?
You're muted. Go.
I'll eat them. Alrighty. Thank you.
All right. Good night, guys.
Good
Right,
night.
thank you.
Have a
Thank
good
you.
one.